Locomotion-aware foveated rendering. In this paper, we propose the locomotion-aware foveated rendering method, for exploring VR scenes using different locomotion methods, to accelerate foveated rendering performance without sacrificing the perceptual visual quality. Firstly, we analyze the viewing motion when using different locomotion methods exploring VR scenes. The viewing motion includes gaze motion and head motion. We divide the gaze and head motion into 5 states. Static, vertical motion, horizontal motion, positive oblique motion, and negative oblique motion. We capture the user's gaze motion and head motion data when exploring VR scenes using joystick moving, teleportation, and redirected walking. Then we plot the frequency histogram and confusion matrix of the gaze motion under different locomotion methods. The frequency of gaze staying still is much lower under redirected walking than joystick moving and teleportation. And the gaze motion is not in static state frequently under redirected walking. For all locomotion methods, gaze tends to stay still, move horizontally, or switch between the 2 states. The frequencies of head staying still are much lower under redirected walking and teleportation than joystick moving, and the head motion is not in static state frequently under redirected walking and teleportation. Head tends to move in other states from horizontal motion, or back to horizontal motion from other states. The sensitivity of HVS varies with gaze and head motion. For those locomotion methods in which the user's gaze or head motion are not in static state frequently, the rendering quality of the foveal region can be reduced to a certain extent without sacrificing the perceptual visual quality. And reducing the shading rate decrease speed in the peripheral region can improve the perceptual visual quality. In this paper, we propose the locomotion-aware foveated rendering method based on the log-polar mapping foveated rendering framework. It uses the foveal average shading rate control coefficient alpha, to control the average shading rate in the foveal region. When alpha decreases from 1.0 to 0.85, the rendering quality in the peripheral region is noticeably improved while maintaining the foveal rendering quality. The peripheral shading rate decrease control coefficient beta controls the shading rate decrease speed in the peripheral region. When beta decreases from 1.0 to 0.7, the rendering quality in the peripheral region near the fovea is noticeably improved. The overall shading quantity control coefficient delta controls the overall shading quantity. When delta increases from 1.8 to 2.6, the rendering quality decreases in both the foveal and peripheral regions. We optimize the locomotion-aware coefficients for the locomotion-aware foveated rendering in pilot user studies. Firstly, we find the highest foveation level that has no significant difference with foveation level L1 for each locomotion method, so as to evaluate delta for each locomotion method. Then we optimize alpha, beta, and define delta for achieving the similar perceptual visual quality as the conventional foveated rendering with the maximum rendering acceleration. The locomotion-aware coefficients alpha is 0.85, beta is 0.7, and delta is 2.0 under joystick moving. Alpha is 0.85, beta is 0.7, and delta is 2.2 under teleportation. Alpha is 0.85, beta is 0.7, and delta is 2.4 under redirected walking. We visualize the rendering results of LAFR with optimized locomotion-aware coefficients, and LMFR with the same rendering performance as LAFR, under different locomotion methods in dining hall. For all locomotion methods, the rendering quality of LAFR is significantly higher than that of LMFR. Since the sensitivity of HVS gradually decreases when using joystick moving, teleportation, and redirected walking exploring VR scenes, LAFR can reduce rendering quality gradually under teleportation and redirected walking without sacrificing the perceptual visual quality. We compare the perceptual visual quality among the full resolution rendering method RR, the locomotion-aware foveated rendering method LAFR, and the conventional foveated rendering method LMFR, For exploring scenes using 3 different locomotion methods, p-value and Cohen's d both show that the perceptual visual quality between LAFR and LMFR is similar under all locomotion methods. The probability of the score greater than or equal to 4.0 for RR, LAFR, and LMFR exceeds 85% under all locomotion methods. The average FPS of LAFR for all scenes is 129 under redirected walking and teleportation. LAFR achieves 2.86 to 3.75 times speedup compared with RR, and achieves 1.41 to 1.61 times speedup compared with LMFR. Since higher rendering quality is required under joystick moving, the average FPS of LAFR decreases to 101. Compared with RR and LMFR, the acceleration ratios of LAFR are 2.44 to 2.72 times and 1.16 to 1.18 times. Except for the comparison with LMFR under joystick moving, p-value of LAFR is less than 0.05 for all other comparisons. For the comparison with LMFR under joystick moving, the value of Cohen's d is 0.54 and its effect size is medium. The results show that LAFR achieves significant performance accelerations compared with RR and LMFR under all locomotion methods for all test scenes.